Welcome to the NCT Data Science Seminar Series. The talk is also jointly hosted by Heidelberg AI. We welcome our guest speaker, Kitu, as well Lena Meyer-Hein, the host of today's seminar. The stage is yours, Lena.
Yeah, I'm very excited to have Hido here today. She obtained her PhD from the Chinese University of Hong Kong and then worked as a postdoc at Imperial College London, by the way, supervised by Ben Glocker, who already gave a talk in the seminar as well. And meanwhile, she's an incredibly successful assistant professor with the Department of Computer Science and Engineering at the Chinese University of Hong Kong. She works in AI for healthcare with a specific focus on medical image analysis and robotic-assisted surgery. She already won a number of distinguished awards. I'm not going to name them all. Also served as program co-chair of major conferences such as MICAI and IPCAI Middle. And yeah, what really impressed me probably the most is her age index. So an assistant professor would normally be called rising star, but I think with an age index of 56, I think Hido is actually already a star, maybe a superstar. And I'm very glad to have you here today.
Yeah, thank you, Lena, for the very kind introduction and the invitation. So let me share my screen. Okay, can you see my screen now? Okay, great. So thank you very much again for the nice introduction and the invitation. So I have been following this seminar series myself as well. So I watched the videos online, and now it's my turn. Very honored to be here today to share some of my recent work on image-based robotic surgery intelligence. And so I did this mainly for this particular topic, starting from my faculty position, that is a joint appointment in Department of Computer Science and Engineering and the Robotics Institute and here at CHK. So since then, I started to apply the AI in the robotic surgery and surgical data science kind of field. And as we all know, for this minimal invasive surgery is increasingly adopted in the daily use of operating room. And here is the photo that I took myself. The first month I started my position, and then I went to visit the hospital and I see how they work there. And this is their daily work with many advantages. I don't want to mention here because we all know that's the benefits of this kind of new format paradigm for surgery. And here, when consider like what to do or what to choose, which part to do, then we'd say what is the challenges and opportunities for a certain topic. And here in particular for the robotic assisted surgery, the third one is a kind of new tool for the surgeons, especially for the current generation of surgeons, and they change from the open surgery and minimally invasive surgery into robotic surgery. And then basically from the clinical wise, at the surgical video or vision-based, image-based is increasingly important, and the use of haptics in the current commercialized surgical robot system make the visual sensory is even more important. And especially for the narrow field of view, of course, given the minimally invasive kind of format. And then the surgeons, they need to learn new skills of how to manipulate the instruments given in the new platform of robot. And also we consider the new ways of coordination or collaboration inside the operating room among different members, including the nurses and the chief surgeons in the surgical team. And this set of challenges not only apply to the very commonly used defensive surgery, but also for some new rising of the new tools, different designs of surgical robots, like the flexible robot and endoscope robot. And this is a single port robot. And here is an example of the robot designed by engineering, mechanical, and the clinical team here at CHK. So this set of new challenges that provides the unmet clinical needs for us as engineers to solve it. And the other side is from the AI aspect or from the computer science aspect of data processing. As we know, the data-driven is important for developing the current deep learning models. And for us, like the surgical data analysis or surgical data science, I believe Lena's contribution to the Indovis series of challenge is a key driving force to promote the field to develop and as a good pace that provide the platform for people to seek the data and also provide the well-formulated, formatted tasks. And here for the technical innovations aspect, there are kind of open problems that we have opportunity here with the current readiness of the methodologies and also the data sources. And one example here is for the cognitive assistance or the context awareness of the understanding of the situation in surgery. And also for the data analysis or data analytics for the new ways of surgical education, here includes some of the AI and also AR and VR techniques for this kind of the use case, and also for the automating of some of the tasks towards the autonomous surgery or semi-autonomous of the surgical steps. And altogether, finally, the value part will have the demonstrate the use case and the values from the surgeon and patient wise to enhance the clinical need and clinical usage. So here in this talk, I follow the three parts, and here are the three parts is also the kind of agenda of my research team here, that how we integrate AI into the concept and field of the robotic surgery to make it more intelligent and elevate level of autonomous and intelligence. So the first one is AI-enabled multisensory perception to improve surgical situation awareness. And this part is mainly for data analysis from the computer vision aspect for video analysis, plus some of the robotic kinematics data. And the first task I have to mention is surgical workflow recognition. Basically, this is where we start from that almost the whole field start to look at this task that's defined by understanding the current status and step of surgical procedure. And this is a well-known data set from Charlie 80 of the different steps of the gallbladder dissection. And the challenges from data aspect is limited like interface variance and symbols and artifacts from the video data analysis aspect. And sort of the first work from the team here at CHK is to develop the SVRC-net that is connecting the convolutional network and the recurrent neural network to extract the spatial temporal information that we studied, developed in 2018. And the key idea, I think, following the idea and for the task of surgical workflow recognition is to consider how to incorporate the temporal information as long as possible, especially make use of the previous longitudinal information to make prediction for the current action, current step. And we have different versions of the algorithm following this idea, including using the non-local operation or memory bag. And here is the transformer-based network to incorporate the previous few minutes length of information and onto current prediction. And this is the current version of the transformer that we published in the MICAI and also extended to IGCAR's journal. And currently, I think in this kind of topic, if given the certain amount of data, for example, a few like around 100 cases kind of thing, and that can achieve the workflow recognition accuracy of around 90. So this is the status and from my observation of the tasks in current status. And we have a use case here for surgical workflow recognition and apply it onto a real-time animal study, and here in a preclinical setting and here at UHK. And this use case is for the procedure of ESD. So it's endoscopic submucosal dissection. So it is endoscopic procedure. So it's not as complex as a so-called a surgery. So my clinical collaborator always let me know that this is the endoscopic procedure rather than you can call it under surgery. And it is a curable procedure to treat early GI cancers, including the stomach and colorectal and esophagus lesions. So that is, you have a long tube that inside into the GI tract, and you have a manipulator here and to the dissection of the tumor. And for this procedure, it has a clear definition of different steps that is shown here as an example. So the first step is marking the lesions surrounding the tumor for different markers. And then the second is for the submucosal injection to inject the salins inside the tumor so that the tumor can pop up to have a better visualization. And then the third step is for mucosal incision, that is to start to do the dissection of the tumor, and finally for the submucosal dissection to cut out the tumor from the surface. So that is the whole kind of the task definition is to automatically recognize at each time point, so which is a current step of the ESD. And for this one that we have collected data set from a local expert who is also a world recognized expert for doing ESD, and the Professor Philip Chu from Department of Surgery and CHK. And we collected 47 data whole videos from him and labeled all the frames for the data. And here is the overall status of the data. That is the developmental training data. And then for the validation data, we have different sightings. One is the data collected from the same hospital, but from another endoscopist. So we call it as validation data, so-called external validation data, part one. And also we have collected data from another hospital in mainland China, Guangzhou, and another hospital in Germany. So that is for the external validation as a whole. Overall, we have the around 2 million frames for training and 1.6 million frames for testing. And this is the distribution of the data frames across different steps. So the major step is the dissection step. So that is the major part of the procedure. And we also define an adult part, adult category for the recognition task. That is the surgeon is or the endoscopist is not doing anything. That is for hesitation or for cleaning of the endoscope, etc. That is so-called the adult thing. And for the framework, what we use here is based on the transformer architecture that I described in the previous slides, and we did some modification in the network architecture in order to make it as a real-time balance between the accuracy and the inference speed. So, and after developing the data sets that we have tested it in the pre-clinical kind of validation system. This is a standard Olympus system for doing ESD. And we have a live pig animal model for doing the experiment. So that is, we have the video data that is exported from the Olympus system. And then that is here, you can see from the endoscopy processor that we have a third-party computer for implementing the AI algorithm, and also give the output of the AI model onto a third-party monitor that can show the real-time prediction here. And we also tested for the preliminary version of the segmentation model as well within this experiment. And overall, here is a running time for each of the component in the whole system, including the I/O and different component of the model itself. And the overall processing speed is here that can reach real-time performance at around 40 FPS. That is, if you see this screen and this screen, there's no obvious latency compared with set by set. And overall, for the performance, and here is the kind of the evaluation from numerical analysis that is over 90%. And here we have designed a summary, automatic generated summary report for the data analysis results, and this is include the visualization of the different category for each single time point, that is from the beginning to the end, and the prediction for each of the steps. And we have the visualization to compare for different trainees. And also we calculated the time duration for each of the step and consider the surgical skills to have a relationship with their time consumption for each step. For example, if the trainee has a faster operation on the dissection step and shorter for the adult part, then it indicates the higher level of skill. So this design is based on the discussion with our clinical collaborators. And this whole report is based on a template that we insert the analysis result into it, rather than using any GPT-related things to generate this report. Okay, and for this work, we also collected data from different hardwares. That is this model that in Hong Kong we developed using Olympus system, and we collected the data from Guangzhou, China, the hospital that using the Fuji system, which is another system, but has not too often used in Hong Kong. So we collect data from another city. And also we have data from Olympus system from our collaborator in Germany as well. And here we can see this is the result from the Hong Kong cohort. And here are the ROC curves from the two external validations. And overall, from a numerical analysis, that we can see overall for different phases that the accuracy or the AUC can have around over 90%. And for this level of performance, that our clinical collaborator will be kind of satisfied with the current performance, and we are looking forward to have further validation, not only for animal but also seek some of the human trials for this workflow recognition. And following this, using this same use case, we also tried to see if the AI model or if the cognitive assistance can have some of the guidance rather than just recognition. And this is a very initial trial of testing the idea of whether we can learn from the pattern of dissection trajectory by watching expert video data. And this method is imitation learning. That is, we have the video clips, and we also have the labeling of the trajectory for the video clip. For example, we have 10 seconds of video clip, and so that we can see how the instrument is dissecting along a trajectory, and that is labeled. And we use this labeled paired data of video and the trajectory to train a differential model that is a conditional action sampling from the differential model. That is so-called the kind of using the differential model as a kind of the generative model to generate the policy. So the state action pairs are given from the video data, the video frames, and also the trajectory, and then we can sample the sequence of the action and state by using the differential model training, and that is conditioned by the training data. And then this is a implicit different policy, the so-called implicit, that is the different model is considered as a policy generation by the latent neural network. So that is an implicit rather than explicit policy learning. And so by this kind of training, that we can have the model to have a ability to do the prediction for the trajectory given a current video frame. So this work has been early accepted to MICAI this year. And here are some of the results that we have obtained so far. So for the training data, we manually labeled 1,032 video clips, and each video clip contains 3 frames and 2 FPM. So that is 1.5 seconds in total. And then for the dissection trajectory, that we label it as a pointwise polyline. So that is, we have different steps on the trajectory, and then that for each step, that is a prediction for the policy and trajectory. And the prediction is for predicting into the future for the trajectory. That is, we cite here and 3 seconds. So for the experiment, we have 2 contexts for validation. One is, we call it as in the context, that is for the training data. and testing data come from the same patient, but different time point and the procedure. This is to validate, this is a relatively easier situation. That is, we have a relatively similar background for the trajectory prediction from the training data and testing data. And the other is out of context. That is training data and testing data of the video clips come from different patient. So it's likely that the surgical scene, we have different, but not completely different. It's kind of not exactly the same scene distribution. And for this tool, that the observation so far is that the model has a kind of capability to predict at least the direction of the dissection, and also the prediction here. The green line is the ground truth from labeling, and the yellow line is the predicted. So that is, they are kind of close to each other, and to indicating the direction and angle of the dissection. So this is the current results that we have, and I personally feel that this part of direction that is interesting, and imitation learning has been used a lot in the general robot situation, but not yet a lot in the surgical situation. And here we have some initial testing that it can have some reasonable results so far, and some more elaborate method design and comprehensive evaluation will be on the way. And the next step. And with here is this slide is to extend from excuse me. So extend from the pure video analysis into the multi-sensory perception. That is, we not only have the image data, but also has the kinematics data that is acquired from the robot. So that one is basically for the image data, and the kinematics data from robot are synthesized, and that include information not only for the position of the instrument, but also for the action aspect. And this information can be combined together, and the kinematics data is robust to the scene variations like the smoke and the blur, and that can enhance the robustness of the models. So this one is a use case that we developed for the surgical action recognition using the ex vivo dataset of suturing. And here is that we have the video data and the paired kinematics data for the multi-sensory perception. And then we have the feature extraction separate in the beginning because the data format are different. So we need to map the raw data into the latent space for feature representation, and then fuse the different modality of data in a graph neural network. That is a relational graph, relational convolutional graph convolutional neural network to fuse the hidden states from the visual features and the kinematic features. And here we separate the left hand and right hand for the information fusion. So that is basically we assuming that for these hidden features that it is extracted from each of the modality, then they have a representation to model the what action that is being done. And then by using the fusion of this information, that can further enhance the reliability and enhance the discrimination capability of the model to do the prediction for the final task. And here the idea is to use relational learning. That is, we have the different definition of the relations between the multi-sensory data. That is, we have the vision to motion relation, motion to vision relation, and in between the two hands of the motion relations. And here, the use case is very simple. That is suturing. Is a JAXA dataset released by Hopkins University many years ago, but people always keep using this because kinematics data is very rare, that not many people is releasing that. And here is results, and not only seeing the results from this model, if we see the results that from all the methods that we can find that adding the kinematics data that is helpful compared with only using the vision data. So that is the kind of the observation that we can have from this work. And for this one, we tested the graph model for the workflow recognition or for the action recognition on 2 sets of robots. This is a collaboration with Hawkins University, with Matthias and Russ. So this is the task of pack transfer. That is a very standard task for surgical robot skill training. That is, you pick up this pack from one place and then you hand over from one hand to another hand and then put it onto the other targeted pack position. And then we manually labeled the data and collected 2 sets of data for the Davinci Research Kit and CHK and Hopkins. And we apply the model, the same algorithm on 2 sets of the hardware platforms. And so far, here are the results of the demo here. That for this very simple task, the model can achieve kind of 100% accuracy for both of the robot. So this is a thing that we consider as important to validate, at least to test whether kind of the AI algorithm can be applicable or is robust enough to data collected from different sets of robots. So because when we touch some hardware, that is lots of uncertainties, and it's very important to see beforehand whether this kind of algorithms, data-driven algorithms, is robust to this kind of, or is generally applicable, or can accommodate the change or differences of different robots. And this is a work that is from the ex vivo toy example to the in vivo procedures. And this is a work that a fresh work published, accepted to this year's Arrows, and the conference is on this week. So that is presenting it now in the conference. So this is for the surgical instrument segmentation, especially for the tape part of the instrument. So instrument segmentation has been studied for a long time, that is also a standard task. And for the segmentation of the shaft area and wrist area, already good enough, I think. There's around 90 deaths. But for the tape part, it's the most challenging part. And current the lowest performance is for the instrument segmentation is whether can have accurate recognition of the instrument tape. So for this one, that we use multi-sensory visual kinematic data to do the segmentation of the instrument tape. And this data comes from our collaborating company in China that they very generously share with us for the video data and kinematics data from the robot. And the idea here is that with the kinematics data, and we can know the relative position of the instrument with respect to the camera in the 3D coordinate space. And we can also have the instrument CAD model of each of the instrument in the scene. So by using this, we can use mesh rendering to map the CAD model according to the kinematics coordinates onto the image, so that we can have a rendered mask in the image. And then this rendered mask can relatively tell us the location of the instrument onto the image, as shown here. So the right image is the rendered mask by using purely the kinematics data and the CAD model of the instrument. And the left image is the ground truth label purely from the image in itself. So we can see that the orientation and location of these 2 source of information generated the mask are kind of aligned, but they are not exactly the same because the instrument is table driven and the kinematics not 100% too accurate, and then that has kind of the error or that is a system error when do the mapping. So that is not directly usable if you do the mapping here. As you can see here for this example, this is a mapping from the kinematics and this is from the image. They have some kind of shift comparing with 2 of them. But this kind of information that is mapped from the kinematics data is helpful to provide, at least for the topology connections and geometry information and orientation of the instrument. And this information can be used and modeled inside the neural network. And here again, we use a graph neural network, considering to model their topology and geometry coordinates rather than the spatial coordinates, so that we can propagate the features from the orientation of the rendered mask onto the image features by using the cross-model graph contrast. And then this can help enhance the representation capability and reduce the false positives of the instrument tip segmentation and the prediction. And for this one, that we designed the experiments as the new one procedure auth validation in order to validate whether this kind of segmentation is robust and the kinematic information can help bypass the change of the background, and so that we can accurately segment the instrument regardless of what is the new thing that comes in. And for this one, that we have collected data for multiple procedures, and most of that is from the cadaver experiments, and one is from the PIC, the proctal experiment, and for the procedure that include the gastrectomy and Fox duplication, etc. And here is that we have a total of 6, and then for each round, we have a total of 5, and for each round we keep use 4 for training and the remaining 1 for testing for the leave 1 procedure auth validation. And here is the segmentation results, and we compare our method with the current image segmentation methods, and this method is using the vision kinematics method, and we re-implemented our own data set. And so far, the performance improvement is significant, but if seeing the performance in itself, there is still a gap that needs to be improved compared with the segmentation accuracy so far for the shaft area and the major joint area of the instrument. And here is some of the visualization results that we compare the results for different methods. Then this is a ground truth, and this is the rendered. This is the rendered mask, and here is the final segmentation results from the multimodal sensory perception data. And here for the pure image based, they're likely to have some false positives. But if you have some prior that is propagated from the kinematics, the location information has a strong prior to rule out those false positives. And that is the thing. And so far, my team is also driving some of the data release as well, because we do need a lot of data in the field so that more people can come in to work together on this field of topics. And this one is the data that we released the last year, Mikai, and it is for the purpose of image guided surgery. That include laparoscopic data, video data from hysterectomy, and we also have the data of robotic data of the movement for the robotic camera in order to have the low-hanging fruit of autonomous hand holder of the endoscope itself. And this data we have labeled the workflow of the hysterectomy and the instrument of the hysterectomy, instrument of the thing, including the instrument and also the K autonomy in the surgery. And we also have the release for the kinematics data from the robot, in particular for the camera movement of the robot. And this is another one that this year for the data set of the foundation model purpose, and we organized the 9 public data sets of endoscopic videos, including the colonoscopy, trastoscopy, and laparoscope. And we also added our private data set collected from our collaborator from Shanghai, China, and that is supplement basically a large number of the endoscopy video data, including colonoscope and trastoscope. And overall, the overall data set include 33K video clips and 500 million frames for doing the pre-trained model or foundation model. And not all the data are labeled. So the public data are very well labeled, and for the private data are not fully labeled. So that is why now that we develop self-supervised pre-training for the foundation model. And the purpose of the model is to make use of the large amount of data and to capture the spatial temporal information inherent in the endoscopic video. And we designed a self-supervised learning mechanism to have the augmentation from the temporal space, that is, we randomly sample the video from different FPS frames per second, and then that is to make the output as consistent regardless of the speed of the video. And we also have the spatial augmentation of cropping the area inside in the field of view to different sub crops, so then to have the model prediction to be consistent as a contrastive learning. And this whole training mechanism or training paradigm is using the student and teacher scheme. So this is a standardized self-supervised learning, and this part is nothing special. And for this foundation model, we have used it to test on 3 downstream tasks, that is including the classification model, segmentation model, and the detection model. And this is the results that we have obtained so far, that it can perform better than the auto-box foundation model image analysis models on the endoscopic video analysis, and it can also outperform or have at least a similar level of performance for the STEM model on the segmentation task from our testing, but we are using the much less data and the specified use case for the endoscopic data analysis part. So we have released all the models for each of the tasks in the GitHub, and all the organized the data set, including the regional data set from the public hospital and our organized data set and pre-processed data set all in once, so that hopefully that this can facilitate people that to have some testing and further develop their own foundation model based on this data set. So that is the first component, and that is also the major component part that my team, my lab here is doing for the surgical data analysis, video analysis. And besides that, we also have some other things that initial exploration, but that is also, I feel, is interesting and important in the long run. And one is for the data analysis for education purpose, and here the use case is for the 3D reconstruction. So 3D reconstruction, or so-called SLAM, is a conventional task in robotics and data processing, but previously the method that is using only for the static scenes, rather than considering the very real practice that we have the dynamics and we have the two-tissue interaction, we also have the two occlusion on the scene. And this is the motivation that I want to have the reconstruction that directly face with the real challenge in the practical data. And starting from there, the first trial is to use the traditional pipeline of the work of the 3D reconstruction. That is, we first have the depth estimation from stereo image, and then initialize the surface from the depth estimation of the scene, and then do the dynamic reconstruction by considering the camera motion and tissue deformation and fusion over time to do the reconstruction. And here is the work and the results, and we obtained from Mikai 2021. And then that we can see that over time that the scene can be progressively filled by using the temporal information to accommodate the occluded areas. And also we can real-time monitoring the depths of the scene by using the transformer-based depth estimation from Hopkins University's work. And here we also validated the robustness to some of the blurred scenes and smoke scenes. And then later on, we try to use the near-random nerve-based model to redo the same task by using the generative capability of the scene representation capability of nerve-based methods. And this one is that we formulate the scene representation and the canonical space of the soft tissue scenes and situation, And then here, the thing that the most novel part that we added onto the nerve is that we incorporate the occluded areas by using the retracing and recasting to bypass the occluded areas. That some of the areas can be seen over time, and some areas are always occluded, so that you can use the generative capability of the networks to incorporate or to accommodate these occluded regions. And here are some of the results that the current methods have so far. So that this is compared with the previous methods from last year's Mikai, and this is the recent the nerve-based method. That is, since it's a kind of a rendering method for visualization, so we could see that the surface and visualization is kind of smooth, and also the modeling of the deformation is smooth and consistency based on the capability of the generative ability of nerve in itself. And it also can handle the large topology change. If we have the cutting twice of the tissue, it can also trace the change of the deformations. And here are some more examples here. So for the nerve part and this work that we have these results last year, and then since then we continue to move forward for this one, but we feel it's a challenge as well by moving forward this direction. And currently what we are doing is two aspects. The first one is to speed up the nerve training. Currently for this particular Mikai method, that is trained for a few hours, and currently we are shortening this method into within half an hour, but that is still too long to train for the real-time performance, so that we are considering the downstream task for using this nerve reconstruction as a simulation purpose. That is, we can convert the data from the stereo video into a 3D surface for the data generative simulation purpose for navigation or robot learning. And the other one that is related for the education purpose is to use augmented reality for remote mentoring. So the idea is that we have the surgeon side, the trainee side in the operating room that's seen through the console, and then the thing can be transmitted to the remote mentor side, and the mentor can see through the HoloLens and then have hand interaction in his or her side, and then transmit back to the guidance onto the console, so that can change the traditional verbal mentoring into the explicit demonstration of the trajectory from the AR aspect. And here is the pipeline that, for example, we can see the console scene here in the surgical field of view, and then this thing can be transmitted out in real-time transmission with a compressed 3D scene, including the stereo images and dispositive map, and transmitted out to the remote mentor side, so that the mentor can see the reconstructed 3D surface through the HoloLens for the 3D visualization. And then the mentor side can also use the pure hand interaction to do the demonstration. For example, here is to draw the trajectory using the needle. And this demonstration can be traced and also provide explicit guidance to the current scenario and transmitted back to the console, so that this is the demo that is directly visualized in the console using the temporal mode of DaVinci Robot, so then the trainee can just follow the trajectory explicitly for a kind of more direct and explicit guidance. And the whole thing, the whole pipeline from here transmitted data to the mentor side and transmit back has to be completed in real time, or at least there is no obvious latency from the user experience. And here is a kind of a pipeline for doing this. That's the most of that is engineering aspect rather than novel like AI algorithms. And then the key part is to have the compressed data flow, that we need to compress the color image and also the dispositive image, so that we can not lose the 3D spatial information for 3D reconstruction in the HoloLens part. And the other one is for here is we have the hand-based gesture, and to recognize the gesture of the hand for interaction and trace the movement purely based on the hand interaction. And we are having the use case for this set of the the system AR mentoring system for the use case of the head and neck surgery that it have very narrow space in the operation. And here is a demo that briefly show how the system currently can work. And you can see this is the original scene of the console side, and this can be streamed to the remote mentor side seen from the HoloLens. And can have the 3D visualization, can also have the 2D visualization, whatever. And then this is the demonstration here, and that can be traced back, mapping back to the guidance overlay back onto the trainee side inside the console of the DaVinci robot. And the last part is the AI-driven embodied intelligence for surgical task automation. That is to have a simulator to train the surgical robot to complete certain tasks automatically from the perception and policy learning and the execution. And this is challenging mainly not yet from the AI part, but from the simulation part. That is the current robot learning simulators for the general robot is not applicable to the surgical robot. And some of the very good efforts from the field from the UCSD and Hopkins and the University of Verona has already done good work and contribution to the simulator side in the field. And from me, my aside that we also tried to develop a simulator, we call it Thorough. So it is a RL-centered and the DVRK compatible simulator for the surgical robot learning. So the concept is that we need to have a digital twin of the surgical robot, including all the kinematics, the movement, and the 3D models, okay, of the objects inside the simulator, so that what it learned inside the simulator can be transferred back to the real robot for demonstration and transfer learning. And also what's the data collected from the real robot can be devoted into the simulator easily for learning from demonstration. And for this simulator, we have already open sourced it through the DVRK software ecosystem, and it has already been used by some of the colleagues in the field already to do reinforcement learning based method development. And here is a general framework for the concept and the composition of the simulator. That we have the haptic input part for the human demonstration, and we have the policy learning part for the algorithm development, and also the embodied environment for interaction, including the visualization engine and physical simulation for the interactions and surgical task design for the use cases. And we made the design of the simulator of each component as relatively independent, so that we can the maintenance for each individual component and upgrade for each individual component will not affect too much for the other parts. And so far we can have two sets of the user interface. One is the 3D touch, that is a kind of the low cost device for the manipulating of the virtual objects in the simulator, and the other one is the more domain specific device of DaVinci research kit, so that we can use the MTM to manipulate the instruments of the PSM in the simulator for data collection purpose. And here, so far, that forms the concept of human in the loop embodied intelligence with the interactive simulation environment, that we can have the expert data collection, and then that can have interaction in the simulator, and the simulator itself can provide feedback for the agent learning for trial and error based on exploration and exploitation. And then that can have a policy learning for the task automation, and that can be executed back into the robot through the digital twin concept. And here are some of the use cases so far already included and released in the simulator that we designed different tasks according to different level of difficulty. One set is a fundamental action task, including you reach the needle or you pick up the gauze, and also you hand over the needle from one hand to the other. And also for the endoscope camera control, that is how to manipulate the endoscope in order to achieve a desired angle for the optimal view. And also the last one is surgical robot skill training, following the curriculum of robot skill training, including the pack transfer and needle rings and pick and place, etc. So all these tasks can be freely conducted through the haptic device for the user interface, or can use the script-based generation to generate the trajectory inside the simulator for training purpose. And we designed some of the reinforcement learning algorithms to automate this task included in the simulator. And one here is for the demonstration guided reinforcement learning for efficient learning from the exploration of task automation. And that is basically we collect the data from the simulator, and then that can get the exploration process inside the simulator, so that can reach the optimal policy and agent by using the actor critic framework, which is a state-of-the-art reinforcement learning framework so far. And the next one is to touch the task of the long horizon task learning. That is, we not only have just one episode of action, but we have a series of actions to complete the whole chain of the task. So that in this case, we can automate a level of the complex tasks that has different steps. For example, here we have the biomanual pack transfer. Then we can decompose the task into the, you flip or you use the manipulator to grasp one of the pack, and then you hand over to the other hand. You put the pack into another targeted position. And also for this one, you have the biopack board, and you have the ring, and you hand over, and then you put the ring in the desired place. So such kind of the long horizon tasks can be designed by using the value informed skill training. That is basically we need to learn the policy in order to determine which is the end state or the terminal state of the intermediate subtask is a good state of the next step of the subtask, so that you can chain the whole series of actions to complete the whole task. And the next one here is the fresh one.
Sorry to interrupt you, but there's already quite a few questions in the chat. Can you maybe wrap it up so we have time for questions? Sorry to interrupt you.
Yeah, I know. So this is almost the last few slides. But I'm monitoring the time. So so this one is the work that we are using the GPT based the architecture backbone for decision making. That is a goal condition decision transformer. It's a sequence in, sequence out kind of decision makings. And here, since it's a kind of large scale model, so that we can train multiple tasks together in one single model, and then have a little bit fine tuning for the downstream task. And this is so far the policy learning accuracy for all the tasks included in the for most of the tasks, not all, most of the tasks included in the simulator so far. And for some of them, that is already very good. And for some of the relatively complex tasks, there is still a long way to go. And here are the demonstration of the learned tasks that inside the simulator, that all the things is automatically executed. And for this one, we also need to
on the Da Vinci research kit.
We also need to execute the policy on the real robot. So that is for this one is a needle pick, and here is for the single hand pack transfer to execute the learned trajectory on the DRK platform. And here are the biomanual tasks. So that is we hand over the needle from one hand to the other. And then this is for the bio pack transfer, that is hand over the pack from one hand to the other, and then put it onto the desired position. And this is to do the ring ones, that you have the handover of the ring from one position to the other and put it on the other side. So this is the whole chain that we need to do the training in the simulator and have to validate this kind of policy learning onto the real robot before we can publish anything. So I think that's pretty much for all today. That currently we have the mixture of so many things, including the imaging and learning and robotics. And all in all, we want to have a value and the image-based robotic surgery intelligence and put it into clinical use for different use cases as many as possible. And also want to acknowledge the great support from my institutions and the collaborators, so that we can move faster for this very competitive and challenging field. Okay, thank you very much, and sorry for overrunning the time, and I'm happy to take all the questions.